We will resume our discussion of Prandtl's lifting line theory. This is the slide that we left off with. As I mentioned, we are going to deal with Prandtl's model. He assumed that every span location, there's just a vortex, single vortex at the quarter chord. All this complexity that's going on in real flow, even the reduced complexity that's going on in chapter 4 has been eliminated. We just have one single vortex, which is a function of y, where y is the span-wise direction, so it's changing all along here. If I can somehow solve for this gamma, then I can find my lift. So he assumed that each span station there's a gamma. It's a function of y. That particular line is called a lifting line. It's going to be parallel to the y-axis. We call it a lifting line because all the lift is concentrated on this one point in Prandtl's model. That means you don't get a pitching moment. If all the force is acting just at one point, there's no distribution of pressure distribution, there's no pitching moment. Therefore, Prandtl's lifting line theory will give you the lift, it'll give you the induced drag, but it will not give you a pitching moment. You have to get the pitching moment from some kind of a test data or some other approximation. So what did we give up? We lumped all the vorticity at a single point. We cannot know how the lift is distributed along the chord. Therefore, we cannot compute the pitching moment. So what we should do is after we find the lift, then go to some curve like a CL versus alpha, get an alpha out of it. Then go to a curve of CM versus alpha, pitching moment versus alpha, and then get the CM. So we have to go back to the test data like we were doing in our XFoil project or from XFoil. So you have to come up with the pitching moment that goes with the particular lift. Fortunately, we can at least get the lift and drag per unit span. So once you integrate it, you can get the total lift and total drag over the entire wing. So once you find a sectional lift at one point, what you will do is you will read the alpha that goes with it. Let's say that alpha is 5 degrees. Then you look for 5 degrees, then find the pitching moment. So this is how the pitching moment is found after we have found the sectional lift coefficient or the sectional lift at each station. Why do we care about pitching moment? Because pitching moment causes the wing to twist. So if you have an elastic wing, a nose down pitching moment like this one here will cause the nose to point downwards, the trailing edge to point upwards, basically effectively twisting the wing and making the angle of attack smaller because of the elastic effects. And if it's excessive twist, structurally the wing may fail or break. So we do want to know how much is the pitching moment. So coming back, this is the Prandtl's lifting line. This is one wingtip, y equal to minus b over 2. This is the other wingtip, y equal to plus b over 2. This is my x-axis, going from 0, x equal to 0, all the way to x equal to infinity. This solid black line is the y-axis, going from minus b over 2 to plus b over 2. These are those vortices on the lifting line represented on the wing. So this is what we are trying to solve. These are trailing vortices that are bringing circulation. When they are coming towards it, think of it as a right-hand screw rule. Depending on which way you are turning the screwdriver, you are moving either forward. So that's what's happening. Circulation is being brought. If you're spinning the opposite way, you're moving backwards. Circulation is being removed. So you're adding circulation, you are removing circulation. By the way, if you have a flap or something you're deflecting here, remember locally the camber line will change a lot. So you'll get a huge amount of extra lift. Therefore, this vortex will be very, very strong, highly visible. Next time when you fly, look up at the window, at the flap edges. when you're getting ready to land, you will see a strong vortex coming off the flap edge. That's this vortex that will be coming from the edge of the vortex flap. It could be your engine on fire, but most likely it's a flap edge vortex. These flap edge vortex, by the way, make a lot of noise. So during takeoff and landing, people are worried about noise generated by high lift devices. That's a different story, different course, different set of tuition fees. Now we are going to take one single vortex of these. There's infinite number of them. Okay, this is really a vortex sheet. There are lines of vortices running from the wing to the infinity, all the way, wing to the infinity, because the airplane is infinitely far away, relatively speaking, from where it started. So these lines are going from x equal to 0 to x equal to infinity. So if you take one particular vortex, it's either bringing circulation towards the wing, so think of it as a screwdriver advancing in this direction, or it's taking away circulation, that means a screwdriver spinning in the opposite direction. Either way, it's got some strength called delta gamma, which is a change in the gamma between one part of the wing and the other part of the wing. So it's got a strength of delta gamma. Let's say this is a y equal to y naught. Okay, your origin is somewhere here, so we are measuring the origin from here. So origin all the way to this particular lifting, this vortex, infinitely small, weak vortex of strength delta gamma. This whole distance is y naught. The point itself is at y. So the relative distance is either y naught minus y or y minus y naught, depending on where the origin is located. For example, if the origin was located here, this would be y, this would be y naught, therefore distance will be y minus y naught. The main thing is the distance between the vortex and the point on the lifting line. So what we are going to do is we are going to compute the downwash at the point P due to one of these vortices, then integrate for all such vortices that form from wingtip to wingtip. So we are going to take one infinitely small vortex, find the induced velocity somewhere on the wing, then we are going to sum up similar induced velocity from all these vortices. So that's what we are going to do. That's what Prandtl did. Now, induced velocity in 2D is gamma over 2 pi r. This is a building block solution that we saw in chapter 3 of our book. So why is this? Because circulation is velocity times the distance. So v theta times 2 pi r, which is the circumference, equal to gamma. So this is what we get in 2D. Now this is you could think of this as a 3D vortex. Vortex is coming towards you, perpendicular plane of the paper, all the way to plus infinity. If you go, it also goes into the plane of the paper all the way to minus infinity. So this particular vortex, if you think of this as a y-axis, and if you think of this as a z-axis, is going from x equal to minus infinity to x equal to plus infinity. So the vortex is infinitely long in a direction perpendicular to the plane of the board, plane of the paper. So this is what we learned in 2D theory. So it goes all the way from one end to the other. But in our lifting line theory, it starts at x equal to 0 and goes to x equal to infinity. Therefore, we have only half the length of this 2D vortex. So what Prandtl said was, instead for 2 pi r, I'm going to make it 4 pi r because I have only half the induced velocity coming from the vortex. My vortex is half as long, so it's going to produce half less the velocity, induced velocity. So rather than using a 2 pi r, he used 4 pi times r, where r is simply the distance between the vortex and the point where you are computing the downwash. So if the vortex is placed at y, if the downwash is placed at y naught, at point P is y naught, this relative distance is y naught minus y, assuming origin is somewhere to the left. Okay. So this is the downwash. So all you have to do is integrate this from minus b over 2 to plus b over 2 to get the downwash from all the trailing vortices that we saw here. So the total downwash is from the wingtip to wingtip of d gamma over 4 pi times r. R is the distance between where the vortex is placed and where the point is located. So this is the downwash at the point P on the wing, is this integral. 4 pi is a constant, so I can bring it outside. D gamma can be written as d gamma over dy times dy. So this can be done. So we are going to continue with it just a little bit more, then we will take a break, then continue with it. So what does this downwash do? What it does is, if this was the original free stream velocity and if this was the alpha, the downwash has changed the effective direction of the flow. Therefore, the alpha now is not the full alpha, but alpha, full alpha, minus this small angle. The small angle is called alpha I. This is arctan of this downwash velocity divided by free stream velocity. It turns out this is a very, very small number. This is usually tens of meters per second. This is hundreds of meters per second. So a small number can be replaced by that number itself. Arctan of a small number is number itself, as long as we are talking about alpha in radian. So this is called the induced angle of attack. So all we have to do is CL equal to 2 pi times alpha minus alpha naught minus this induced angle of attack. All of a sudden we get less lift because we have this extra number here, which was not there in our 2D theory. By the way, A naught is 2 pi in theory. If you measure the lift curve slope like we did in our Abbott and Deinhoff report, we may use the measured slope rather than the 2 pi. Either one will work okay. So that's what we'll be doing here. Now, therefore, lift is rho v infinity gamma. So we put a lift here. Kuta-Joukowski theorem says this is your L prime. L prime is 1/2 times rho v infinity squared times chord times lift coefficient. Lift coefficient is A times alpha minus alpha naught minus alpha I, as you saw in this picture. A naught or A, we could use either symbol. I should have used the symbol A naught, my mistake. So I call it A here. It's really A naught. A naught is the two-dimensional lift curve slope, which is a function of, which is independent of the camber line shape, but this alpha naught is a function of the camber line shape. So which aerofoil you're using, where you're using on the aerofoil will show up through this alpha naught. How is the wing twisted will show up in this alpha. Okay, because if you twist the wing a lot, you're going to get a lot of alpha. If the wing is twisted less, you're going to have less alpha. So wing twist shows up here, camber line based angle of zero lift shows up here, downwash is here, gamma is here. Now I can bring the W to one side, take everything to the other side, I get this relationship. All right. Now rho cancels out, one of the V infinity cancels out, 2 goes to the other side, that's why you get 2 gamma. A naught and C go to the denominator. Alpha naught, W stays on one side, alpha naught goes to the other side. So this is what we have gotten. Now substitute for this W, the integral we had developed up here. So after some algebra, you get this long equation. This is called the Prandtl's lifting line equation. So this is what we are going to be solving in the next couple of videos. And I'm also going to show you one of my MATLAB code called Prandtl.m, where we numerically solve this. Okay. So we will take a break at this point because it's already 15 minutes. So we will